Well, then I'd like to welcome you back to our 6th lecture. Last time we started with discussing quantum computation, and in particular what we started with was a definition of a qubit, which is the quantum analog of the bit. And we described the qubit, and we've seen that any state of the qubit can be represented by a 3-dimensional vector. And that this vector has length smaller or equal to 1. And we've seen that the equality, meaning that the length, if the length of the vector equals 1, then it describes a pure state. And since we can describe this by a 3-dimensional real vector, we can illustrate this in 3-dimensional space. And there we found this illustration of the Bloch sphere, right? That the states of a qubit, they live at the Bloch sphere, and pure states live on the surface of the Bloch sphere, and if we have mixed states, then the states live within the Bloch sphere. We then described quantum operations, or quantum gates, on single qubits, and these are simply unitary operations which correspond to a rotation of this Bloch sphere. And at the end, we then described also a 2-qubit operation, the so-called CNOT-gate. So let me briefly recall the CNOT-gate and then continue with today's lecture. So last time we had the CNOT-gate, and the CNOT-gate, we had this matrix representation that nothing happens if the first qubit is 0. Well, if the first qubit is 1, then the second qubit flips, right? So in the subspace where the first qubit is 1, something happens. Here, this is the X gate, and here's the identity because nothing happens. And we illustrated this with this circuit diagram, which is equivalent as a controlled X gate. And this matrix representation, so we had first, how does it act? See if the C0 acts on, say, on the qubit state AB, then what we get is A tensor B, and then addition modulo 2 with a B plus A. So where A and B are in 0, 1. Okay. And then we had the remarks. We started with one remark, namely the representation that we use here. So this is the standard representation. We say 0 is equal to 0, 0, which is a vector, so which has entry 1 in the first entry and otherwise zeros. And then we have 1, which is equal to 0, 1, 0, 1, 0, 0. And then 2 equals to 1, 0, 0, 1, 0. And then similar to 3, which is equal to 1, 1, represented by this vector. So this is the standard representation, and works similar if you go to more than 2 qubits. There's a question?
I think there's 1, 0 too much for the first.
Yes. And okay, then last time there was also one thing I missed, an I in the formula of the Pauli matrices. So it was indeed, I think it was sigma j sigma k, which is equal to djk times the identity plus, and here's an imaginary unit I, and then the sum, and then we have the Levi-Civita symbol epsilon j k l sigma l. Okay, so this I was missing. Now let's come back to the CNOT-gate. So the CNOT-gate is indeed an interesting gate because it allows us to generate entanglement. right? So this is remark 2. The CNOT-gate can generate entanglement. To see this, consider, for example, that the CNOT-gate acts on a state, say, A0 plus B1. So we get, and then here we have 0 as the second qubit. So if the first qubit is 0, nothing happens, meaning that we get A times 0, 0. And if the first qubit is 1, then the second qubit is flipped. So we have plus B times 1, 1. And this is an entangled state, meaning it's not a product state for all choices of A and B such that they are unequal to 1. Right? And there you see that we started from a product state. We performed the CNOT-gate, and what we get out is an entangled state. So in general, more generally, what we find is that the CNOT-gate, together with the Hadamard gate, can transform our computational basis states into the Bell states. Okay? So the CNOT-gate together with the Hadamard gate transforms the computational basis states to the Bell states. And the circuit diagram looks as follows. So we have on the first qubit the Hadamard, and then we perform a CNOT-gate. And what it does, it maps 0, 0 to, okay, I think it's phi plus 0, 1 to psi plus 1, 0 to phi minus, and 1, 1 to psi minus. So this is equation 2.24. Okay, so let me now just briefly check the first one, and the other ones you can calculate similarly. So the first one, we start with 0, 0. Then we have at the first qubit the Hadamard, and the second qubit nothing, so the identity. Meaning that we have Hadamard 0, tensor 0, which is 1 over square root of 2, 0 plus 1, 0. And then we have the CNOT-gate. And the CNOT-gate, if the first qubit is 0, then nothing happens on the second qubit, so we have 1 over square root of 2, 0, 0. And if the first qubit is 1, the second qubit is flipped, so we have plus 1, 1. And this is the 5 plus Bell state. Okay, and similar, you can calculate these transformations. Now we can look at the circuit from the other direction. So first, let us recall that the Hadamard gate is self-inverse, meaning that h squared is the identity. And the same applies for the CNOT-gate. So if I apply twice the CNOT-gate, I have the identity. This means that this circuit is self-inverse. And this also means that if I run the circuit from right to left instead, then I perform this transformation in the other direction, meaning that the Bell states can unambiguously be identified by a measurement in the computational basis. Okay. So by running the circuit that is 2.24 from right to left, we can unambiguously identify the Bell states by a measurement or by a projective measurement in the computational basis. And we will describe measurements in the circuit diagram later. Okay, so I hope that you see this here, that since this is self-inverse, if you run it from right to left, then it's simply this transformation in the other direction. Okay, then our remark number 5 is how do I get now a CNOT-gate with a control on the second qubit instead. So a CNOT with control on the second qubit is realized by the following circuit diagram, namely, first I have a Hadamard on the first qubit and a Hadamard on the second qubit. Then I perform a CNOT-gate, and then I Hadamard again. And this is equivalent to a CNOT-gate which has control on the second qubit. And I think you're going to calculate this in the exercise. Okay, then remark number 6. So you see that we are now using the CNOT-gate for some purposes. Okay, the first thing you've seen is that we can generate entanglement. Second, we have seen that we can identify Bell states by a transformation from Bell states into the computational basis. Next, we've seen how we can perform the control on the second qubit, and now we use the CNOT-gate to make a swap of the two qubits. So we exchange the two qubits. So by concatenation of CNOT-gates allows us to swap the qubits and this is done via the swap operation, which has the following circuit representation. So usually you will see this diagram, this circuit diagram, but sometimes it's also we also see such a diagram. And how do you get this from CNOT-gates? So first you make a CNOT-gate, then you make a CNOT-gate with the control on the second qubit, and then again a CNOT-gate. And this, if you want to show this, sit down and do the calculation. It's pretty short, easy. Okay. And what we see is the swap gate. If it acts on a state A tensor B, we get out B tensor 8 at tensor A. Where A and B 0, 1. So you see that we are building up a bunch of useful gates, which we're going to use every now and then. Okay, there's one more remark, which is remark number 7. And this is about a CNOT gate, or a controlled NOT gate, which is now controlled on 0 instead of 1. Okay, so a controlled NOT gate with control on the state 0 instead of 1. Can be realized by the following circuit. So first, we perform a NOT operation on the first qubit, and then simply a CNOT gate, and then again a NOT operation in the first qubit. And now you see, due to this X gate, so the Pauli X gate, performing a spin flip. This means that altogether, this control here, so if we take this together, then the control is on 0 instead of 1. Okay? And this we illustrate by an open circle of the control. So this is the usual gate representation. Okay, so remember, if this control bullet is open, then the control is on 0 instead of 1. But otherwise it works, it's completely similar, as you can see here. Okay, with this we've now seen actually what we've seen is a controlled operation, right? And in particular we considered a controlled NOT operation, but you can now think of, can I have a similar operation, but instead of performing an X gate, could I perform any single body unitary there? And how does it look like? Okay, so this is the next chapter is this is controlled unitary gates. And first, we look at single controls. So here, so far, we have already had a single control, right? But instead of restricting to a NOT gate, we now suppose that we have a control of any arbitrary single qubit unitary gate. So for an arbitrary single qubit unitary gate, U, the controlled U gate is represented by, so we write it as a C of U, means a controlled unitary gate. And in the matrix representation, it's again, if the first qubit is 0, nothing happens. So we have the identity in this subspace. And if the first qubit is 1, then we perform a unitary on the second qubit. So we have here in the subspace U00, U01, U10, and U11. And these here are zeros. Let me again stress here the subspaces. So this is the corresponds to the basis states 0, 0, 0, 1, 1, 0, and 1, 1. Similar here, 0, 0, 0, 1, 1, 0, and 1, 1. So you see that if the first qubit is 0, then nothing happens because I have the identity here. And if the if the first qubit is 1, then I perform a unitary on the second qubit. So it acts as if I have the controlled unitary CU acting on the state A, B, then we get A tensor U to the power of A, B. This is equation 2.30, where A and B are in 0, 1. So you see here that the controlled unitary performs a unitary operation on the second qubit only if A is equal to 1, right? Because if A is equal to 0, we have U to the power of 0, which is the identity. And if A equals 1, then we have U to the power of 1, meaning U, and then we perform this unitary on the second qubit. So our aim now is to find a circuit diagram of such a controlled unitary in terms of CNOT gates in single qubit gate operations. So I actually forgot to write down the diagram. So let me add here the diagram, which is a control on the first qubit, and then we perform the unitary U on the second qubit. So we now want to find a circuit diagram which implements this, and we want the circuit diagram to be decomposed only of CNOT gates and single qubit gate operations. The reason is that we'd like to, so this is what we're going to do next lecture actually, we'd like to see whether there is a set of gate operations with which we can perform any n-qubit unitary, right? So let us now see that there is such a diagram which is only composed of CNOT gates and single qubit gates. And therefore, we use a decomposition that we stated last time. So it's using the decomposition there. Last time we've seen that we can write U as e to the I alpha times A x B x C, where A, B, and C are unitary. And satisfy A times B times C is equal to the identity. So we stated this decomposition last time. Now we use it. And with this decomposition, so it was C equation 2.17. We find diagram that this controlled unitary is equal to the following. So we have here C, then controlled NOT, and then B, again a controlled NOT, and then A, and here a phase gate P alpha. Okay, let's see whether this is correct. So first, let us suppose that the control qubit is 0. Okay? If the control qubit is 0, we know that nothing should happen at the target qubit. So if it is 0, we see that the target qubit, there's an operator C, so the operation C acting on the target qubit, and then here nothing, because the control qubit is 0, so nothing happens. And then we have B acting on the target qubit, and this here again nothing, because the control is 0. And then A is acting on the target qubit, and there's no such phase operation, because if you remember, this phase operation P alpha was 1 and e to the I alpha. Okay, so what we see is, if this control qubit is 0, then we have C, B, A. Okay, and this is exactly what this one does. So we would have first C acting on a state, on the first qubit state, say phi, then B, and then A. And this is equal to the identity phi, which is phi, meaning that nothing happens. Okay. So we just saw that if the control qubit is 0, nothing happens because of this identity here. Now suppose that the control qubit is 1. So if it's 1, then we have first C acting. So then we have an X gate acting on the target qubit because it's a controlled X gate. So it's 1. If the control is 1, then there's an X gate on the target. So we have C, X, B, and then again an X, and then A, and then we have a phase. Since our control qubit is 1, so you see in the subspace where it's 1, we have a phase d to the I alpha. And this is exactly what it gives us. So first C, then X, then B, then X, then A, and the phase d to the alpha. Meaning that this, if the control qubit is 1, then this unitary U is applied to our target qubit. Okay, so it's a nice expression where we see that now controlled unitaries can be decomposed into CNOT gates and single qubit gates. Okay? But sometimes it's the case that you want to perform a unitary gate, for example, on more than one qubit, say on k qubits, and you possibly also want to control this on more than one qubit, for example, say on n qubits. So there you then have n controls of a unitary acting on k qubits. And that's what we discussed now. These are then multiple controls. So it's chapter 2.2.3.2. So often one uses multi-qubit gates. Which condition the execution of a unitary U on k target qubits on the state or on the states in the state of n control qubits. So formally we have the following. So we have a control, now a control on n control qubits of a unitary which acts on k target qubits. So we have then here x1 to xn as the control qubits, and we have, say, psi, which is a k qubit state, and this is equal to x1 to xn, and then we have u to the power of x1 to xn on psi. So let me repeat this. We are now having a controlled unitary operation. The control is on n control qubits. So these are n control qubits, and the control qubits are either 0 or 1, right? And we have as a target k qubits. So this state psi lives in the Hilbert space where we have a qubit and then tensor power k, meaning that we have k qubits, right? And then if this controlled unitary acts, then the control qubits remain unaffected, and the unitary acts on our target qubits, but it only acts if all the control qubits are 1. So if there is a single control qubit, then we have u to the power of 0 and nothing happens. Only if all control qubits are 1, then this unitary can act. Let me now also show you the circuit diagram. So the circuit diagram is we have our n control qubits, and then we have here, so 1, 2 to k target qubits. And now we have a control on each of these control qubits, and they control a unitary u acting on this k target qubits. Okay, this is now a very general description of a controlled unitary operation, right? Because we didn't specify how many controls, and we didn't specify how large the target is and which operation we perform at the target. Now there's one special incident of such a controlled operation with more than controls. It's the so-called Toffoli gate. And so I'd especially like to emphasize this. So a special incident thereof is the Toffoli gate. Or we say it's a CNOT-gate. Or sometimes also called the CNOT-gate. So I put this in brackets. And it is, I usually write C to not. And as the name says, it's a NOT gate controlled by two control qubits. And this is the circuit diagram. how does it act? So we have C2 not acting on, say, A, B, C. We get A, B, and then C and a addition modulo T2 of AB. And this gate is again self-inverse, meaning that if we perform it twice, we get the identity. Now, similar as before, so similar as here, we'd now like to find a decomposition of this Toffoli gate in terms of a CNOT-gate and single qubit gates. And after I erased this board, I just gonna show you this decomposition. It's fairly complicated, at least it seems in the beginning fairly complicated. And if you want, you can check this by calculating this decomposition diagram. You can either use any computational program, or you could sit down and calculate, but I guess this takes a while to calculate. So the Toffoli gate can be decomposed into CNOT gates. CNOT Hadamard phase and T gates as follows. So this is our Toffoli gate. First, we Hadamard the third qubit, then there is a CNOT gate, then we have T gate or the T dagger, the inverse T, and then we have a CNOT gate here with the control on the first, then a T gate, then again a CNOT gate, then T dagger again, then the control not with control on the first, then we have here T dagger and here T, then here a Hadamard, So the proof is an exercise. I think it won't appear on our exercise sheets, but it's an exercise for you. So if you want to check this, as I said, it could be messy to calculate it by hand. If you don't want to do so, you can use a program, so a computational program to calculate it. And then it's fairly easy, right? So if you let the computer calculate it, then it's fairly easy. And at this point, I'd like to make a break. So let us meet in 10 minutes. Okay, let us continue. Before the break, we've seen that, or let's say we introduced controlled unitary gates, and then we introduced also controlled unitary gates with n controls and unitaries acting on k qubits. And we've seen that one special incident, which is particularly interesting, is this Toffoli gate. And there we've also seen that we can decompose it into CNOT gates and single qubit gates. And next, what I'm going to show you is that we can also decompose now a controlled unitary with n controls into Toffoli gates and a controlled unitary gate with a control on a single control. So these Toffoli gates now allow us for a simple decomposition of a controlled unitary gate with n controls. So Toffoli gate allows for a simple construction of a CNU gate by considering n controls, so n control qubits, and additionally n minus 1 so-called working qubits, or ancillary qubits. So let me now draw the circuit for 5, for n equals to 5. For n equals 5, the circuit is as follows. So we have our 5 control qubits, C1, C2, C3, C4, C5. Then we have 4 working qubits, which we initially consider in 0. And then we have, say, our state psi, which are k target qubits. So these are our n equals 5 control qubits. These are n minus 1 equal 4 working qubits. And these here are our k target qubits. And for a bundle of qubits, such as here, we usually denote this bundle of qubits by such a line here. So this means then, okay, there's more than one qubit. Here it can be up to k qubits. And what we want to do now is we want to use Toffoli gates such that these control qubits C1 to C5 control the action of a unitary U on the target qubit. And therefore, we do as follows. So first we have a Toffoli gate which is controlled on C1 and C2, and it acts on this working qubit. Okay. So such that the working qubit goes from 0 to C1 times C2. Okay. So remember, so we have first remember that, so I simply write this down now here. So we have C1, C2, and the target qubit, and then we have our Toffoli gate, so C2U, and then we get C1, C2, and then 0, and the addition modulo 2 of C1, C2, which is C1. Okay, now I must write it down like this. C2, and then we have C1, C2, and then C1 times T2. Okay, this is what this Toffoli gate does, right? And now we have a Toffoli gate with control on C3 and the control on this first working qubit, and it acts on the second working qubit, such that the second working qubit is now in state C1 times C2 times C3. I think I have to illustrate this a bit. Possibly I make it like this. So here, yeah, it's like this. We have the state. No, I have to do it differently. Yes. Okay, let me first draw the circuit, and then I explain it in detail. Then. One, two, 10, 10. Okay, so this is how it looks like now. Let me explain how it works. So the first Toffoli gate sets the state 0 to the state C1, C2. Okay, so here we have C1, C2. Okay, now the second Toffoli gate is controlled by C1, C2 and by C3. Meaning that here we have C1, C2, C3, and then the next Toffoli gate is controlled by this working qubit and C4, meaning that here we get C1, C2, C3, C4, and similar, this Toffoli gate here is controlled by C5 and this one, so here we get C1, C2, C3, C4, C5, and then controlled on this one, we have our unitary. This is exactly what we want. So only if C1 times C2 times C3 times C4 times C5 is equal to 1, meaning only if all these control qubits are 1, we perform this unitary. Right? And then this is what we wanted to do. And the rest of the circuit is simply to reset these working qubits to 0. And the reason why this is mirror symmetric is because we can reset it simply by performing the same circuit from the other direction, because everything's self-inverse here. So the Toffoli gates are self-inverse. So we can reset this. And what we end up with is then, again, these working qubits in 0. And these didn't change, the control qubits. Okay, so this part here, these 4 Toffoli gates are simply there to reset our working qubits. So let me write this down briefly. The first n-1 Toffoli gates they map the last working qubit from 0 to C1 times C2 times C3, C4, C5. Then the unitary is controlled on that qubit, and the last n-1 Toffoli gates, they reset the working qubits. Now, if we take into consideration that we know a circuit for the Toffoli gate in terms of CNOT-gate and single qubit gates, we see that this can all be expressed in terms of CNOT gates and single qubit gates. And for a controlled unitary, we also see that if this target is only 1 qubit, then this can also be decomposed into CNOT and single qubit unitary gates. And so the only thing that remains is then to show that also a unitary acting on many qubits can also be decomposed into CNOT and into single qubit gates, right? And we're going to do this at some point a bit later. What we're going to do now is we now introduce the last component that we need in this circuit diagram representation. Namely, we didn't discuss so far measurements, right? So now I'd like to discuss how we represent measurements. So this is the final element. And what we usually do, and what we actually always do, is we perform measurements, projective measurements in the computational basis. So a projective measurement in the computational basis, or a projective measurement of a single qubit, say psi in the computational basis is illustrated by this diagram here. So we have our qubit psi, and then a measurement, a projective measurement, is illustrated by this symbol. So in the computational, it has the projectors. So with projectors, 0, 0, and 1, 1. These are our measurement operators. Now you might wonder why I said that we only consider projective measurements in the computational basis, but we did learn that there are more general measurements. Namely, we learned that the postulates say that a measurement is described by a set of measurement operators which satisfy the completeness equation, and projective measurements are only a subset of these measurements. And the reason why in quantum computation we only consider measurements in the computational basis, so projective measurements, is that we can perform any measurement by considering additional qubits and then performing such a projective measurement. And actually this is essentially what Neumark's theorem says. So if you remember Neumark's theorem says that any POVM can be realized by extending the Hilbert space into a larger space and then performing a projective measurement, right? This is actually the reason why in quantum computation we only consider projective measurements in the computational basis, because we can extend the Hilbert space by simply considering more qubits and then performing this projective measurement. So, in the theory of quantum circuits, it is conventional to not use any special symbol to denote more general measurements. And the reason is the following remark. That any measurement can be represented by unitary transformations with ancillary qubits followed by projective measurement. and I'd like to prove this now. So the proof, it's essentially Neumark's theorem. So you remember we didn't prove Neumark's theorem, so that's why I now prove this explicitly. And therefore, suppose we have a state psi okay, the state psi can be a state of several qubits, and suppose we want to perform the measurement, the following measurement. Suppose we have state psi and want to perform the measurement with measurement operators M. Okay, and the aim is now to show that this can be done by considering additional qubits, a unitary transformation, and then a projective measurement. So let's introduce ancillary qubits in the state, say 0. So say all of these qubits are 0, and I simply denote this by a 0. So this is also a state of many qubits. And consider the following unitary. Which acts as follows, so that U, which acts on this state psi 0, is equal to sum over M, then the measurement operators M psi M. Okay, you might wonder whether we can find such a unitary, that this is true. And indeed, you can always find such a unitary. I'm going to tell you the reason. So, first note that one can always find such a unitary since, okay, why? Since if I define the matrix, since the matrix M1, M2, M3, and so on, since this matrix, since the matrix has orthogonal columns, which follows from the completeness equation. hence we can find a unitary U is equal to M1, M2, M3, and so on. And we then choose here the elements such that U gets unitary. So we know that from the completeness equation, this M, so this one here, this matrix has orthogonal columns, meaning that we can now choose these columns as we wish, but we have to choose them such that all of these columns are orthogonal and U gets unitary. Right? So meaning that we can always find a unitary such that equation 239 holds. Okay, and now we have this equation 239, and what we want to prove now is that if we perform a projective measurement, that we get out the usual measurement statistics of these measurement operators. So consider the projective measurement with measurement operators identity on the qubits of in the space where psi lives, and then the projectors M on the subspace where our ancillary qubits live. Then first let us calculate the probability. So the output probability is P of M. So we have a trace of the projector 1 tensor M, or let's call this, 1 tensor M. And our unitary transformed state U psi 0, and then psi U dagger, psi 0 U dagger. Okay, this is how probability to get the outcome M corresponding to this projector, right? So we have here this projector, and here we have our state. First the cat and then the bra. And now let's calculate this. So we have psi 0 U dagger, and then this projector 1 tensor M, then the state U psi 0. So now we plug in equation 239. This gives us a sum over M prime of psi M prime M prime, and then this projector, and here we have again a sum over M prime prime, which is the measurement operator M prime prime on psi, and then M prime prime. Okay, so now we can multiply this out. So there's the identity on the first subspace. So this is the first subspace here, here, and here. And the second subspace is this, and this. So we have the sum over m prime and m prime prime of psi m prime, sorry, there must be a dagger, m prime prime psi, and then we have m prime m prime prime. This gives delta functions, so delta m prime m, and this is delta m prime prime. So due to the delta function, our sum reduces to a single term. So we have then psi m prime m psi, which is trace of m dagger m psi, and this is actually what we wanted. Namely, this is now the probability to get the outcome m if we perform a measurement with the outcome corresponding to the measurement operator mm. Okay, this you know. And you see that we get this output probability now if we use additional qubits, so ancillary qubits, perform a unitary operations, and then we perform a projective measurement. So here the projective measurement was only on the ancillary qubits, and then we get out the right statistics. Okay. So this actually finishes the proof. Now let me also show you the circuit diagram of this measurement. So we have our state psi. Again, note this is a bundle of qubits. And we have our ancillary qubit 0, again a bundle. So first we perform a unitary operation on them. And then we perform a projective measurement only on the ancillary qubits. So we illustrate this here with the measurement. And suppose this measurement gives outcome m, so we write an m over this measurement symbol. And then the outcome here is mm psi divided by square root psi m dagger m psi. So let me start this down, where this denotes a bundle of qubits. Okay, so this is an interesting diagram representation, and you will see later on when we discuss some quantum algorithms, then we will see such diagrams or similar diagrams. Okay? Meaning that we perform on the subpart a measurement and we get a state out here. So often it will be the case that it suffices to perform a measurement only on a few qubits, so only on a subspace of qubits. This often suffices. Okay, so this was actually remark 1. Now we come to remark 2, saying that measurement is generally considered to be invertible, so an irreversible operation. So with the measurement, we usually destroy the quantum information and instead get a classical information. That's how we see a measurement in these quantum circuit diagrams. And then the next thing is that measurements commute with controls. And this you're gonna prove in an exercise. So measurements commute with controls. This means the following. So if we have, for example, a controlled unitary and then perform a measurement here, then this is equal to first performing a measurement, and then we have a control of this unitary. And this is also often represented so that the measurement controls the unitary. And here now this double wire illustrates a classical bit. Okay, so we measure, and the measurement outcome then gives a classical bit, because the projective measurement, if we perform a projective measurement in the computational basis, we either get 0 or 1, so we have a classical bit, and this double wire illustrates this classical bit. And here then it says that this commutes, so it doesn't matter whether we first do this controlled unitary and then perform a measurement, or we first perform a measurement and then do this controlled unitary, now controlled on the outcome of the measurement. So the proof is an exercise. Okay, and the fourth remark, I'm going to write it down here, is that any untermined quantum wire is assumed to be measured. So meaning if you write down a quantum circuit and there's a quantum wire without a termination, then you can assume that there is a measurement on this. So you can either leave it open or not. Often people leave it open because it's not of interest anymore. But any undetermined wires, you can assume them to be measured. So this is all for quantum measurements. So in today's lecture, you have seen that we try to decompose those gates always into basic elementary gates, such as the CNOT-gate and single qubit gates. And this is going to be a topic of the next time. So the next time we're going to consider a universal gate set. Namely, what we want to do is we want to show that any unitary gate on n qubits can be approximated with arbitrary precision by a set of gates, namely the CNOT-gate, the Hadamard-gate, and the T-gate. So only by these three gates. CNOT-gate is a 2-qubit gate, and the Hadamard and the T-gate are single qubit gates. And only with this finite set, we will show that we can approximate to arbitrary precision any n-qubit unitary gate. So this is going to take us some time to prove this. And the proof is subdivided into 3 parts. And the first part is, first we're going to show that we can decompose any n-qubit unitary into products of so-called 2-level unitaries. Okay, 2-level unitaries are simply unitary matrices which have non-trivial 2x2 entry, and otherwise it's 1 on the diagonal, right? This is a 2-level unitary. And then we show that any 2-level unitary can be implemented by combinations of CNOT gates and single qubit gates. And as a third part, we then show that any single qubit gate can be approximated to arbitrary precision with Hadamard and T-gate. And with these 3 steps, we then prove that there is such a universal gate set. Okay? And I'd also like to mention already here that we will also see that if we do this decomposition, then we will find out that if we want to decompose an arbitrary unitary, we in general need an exponential number of such elementary gates in order to implement such a unitary. So this is, so to say, it's not efficient, right? If it's exponential in the number of qubits, and this is also the reason why it's not so easy to find sufficient algorithms in quantum computation. But it's important for us to prove this, that there is such an elementary gate set, and then we continue with finding some useful quantum algorithms. So this is all for today, and I'll see you next time on Monday.